Hello, my name is Jim Peterson. I work at Joint Base San Antonio. Joint Base San Antonio is comprised of 7 different geographically separated bases. Camp Bullis is one of those bases. Camp Bullis is a 28,000-acre field training facility located just to the north of San Antonio, on the southern edge of the Edwards Plateau. It is a karst region, where water flowing through the limestone has created caves. There are more than 100 caves on Camp Bullis. "31 of these caves are known to contain federally endangered species, a spider and 2 types of beetles. These karst invertebrates are troglobites. They are adapted for life entirely inside the cave. They have lost their eyesight and lack pigment. Where they live, deep in the cave, there is no primary production, so they rely on something else to bring food to them. In some caves, regular flooding or mammals provide this food. However, in many of the caves, the camel cricket is the main provider of energy into the karst system. Pseudophilus secretus is a trogloxene, meaning it is adjusted to life both inside and outside the cave. It roosts and lays eggs in the cave, but leaves the cave at night to forage for food. In turn, the cricket's eggs, guano, and carcasses provide food for the T&E species inside the cave. The role of the cricket is so important that the U.S. Fish and Wildlife Service uses crickets to gauge the health of the karst ecosystem. And they do this by counting the crickets as they exit the cave. Traditionally, this was done by human observers with red artificial lighting using hand tally counters. Let's watch. That was a video of my first night counting crickets. I remember thinking, this is absolute chaos. Not very scientific. There has to be a better way. Over the next few months, I spent a lot of time in the field observing the crickets, and I conducted a literature review. Based off of this research, we decided that the best approach might be to remove humans from the monitoring process. We turned to the experts at Texas A&M's Natural Resources Institute for ideas, and they suggested the following. Technology was their answer, specifically camera traps. However, we couldn't use a normal off-the-shelf game camera because the target animals were ectotherms, and traditional motion sensing just wouldn't work. So we opted for a high-end camera that was factory focused for close range, with a wide selection of time-lapse and video options. To this, we added a whole package of mounting systems, laser sights, references, and data loggers, collectively called the Karst Invertebrate Monitoring System, or KIMS. The main advantage of this system is that it is accurate. The camera catches everything, and it has replay capability. The use of the camera removes the observer effect, particularly light, which disrupts the cricket's movements. And the camera does not get distracted by external stimuli like weather, animals, or phones. Also, using the system is much safer than having human observers interfacing with deep pits and venomous snakes at night. The next step was to put KIMS into action. We decided to observe each of the Camp Bullis 31 T&E species caves for 2 nights. One night with both a human observer and the KIMS, and a second night without the observer, just the KIMS. So let's take a look at some of the video. This is a video taken by KIMS with a human observer present. The clicking noise you hear in the background is the observer attempting to count the crickets with the hand tally counters. The crickets and mice are aware of the observer and are acting abnormally. The crickets are massing away from the light and are exiting cautiously. Often, they return to the cave in panicked waves. The mice are hesitant to leave the cave and are leaping about, disturbing the crickets. The next video is the same cave without a human observer present. As you can see, the crickets are much more relaxed in this video. There's no massing in the shadows, no hesitancy at the exit, and no returning in panicked waves. Also, there are a lot more of them. The mice have already departed the cave without delay. The ruler near the center of the screen is used to determine the cricket's age class. Adult cricket bodies are 12 millimeters or longer. Subadults are between 5 and 12 millimeters, and nymphs are 5 millimeters or less. In order to quantify what we were seeing in the videos, we had to develop some metrics. Cricket counts are traditionally conducted for 2 hours beginning at sunset. Sunset is assigned a standard time value of 0. First exit is the time relative to sunset that the first cricket exited the cave. In the example, the value of 17 means that the first cricket was observed leaving the cave somewhere between 17 minutes and 17 minutes 59 seconds following sunset. Cricket counts are conducted in 10-minute blocks, and each 10-minute block is tallied for the number of crickets that exited during that 10 minutes. Range is the 6 consecutive 10-minute blocks in which the majority of crickets exited. It is reported as a whole number that corresponds to the start of the range. In the example, range 0 signifies that the majority of crickets exited in the 60 minutes immediately following sunset, whereas range 1 means that the majority of crickets exited in the 60-minute period that begins at sunset plus 10 minutes. Range percentage is the percentage of total crickets counted that evening that exited during the stated range. Now let's take a look at the results. This table has the observation methods on the left-hand side. The values counted for each method are labeled across the top. The first two rows are from the paired night, while the bottom row is from the Kims only night. On the paired night, the observer and the camera counted roughly the same number of crickets, even though the observer's field of view was much larger than the camera's. The real difference between the two methods on this night was between the cricket age classes. The camera captured twice as many nymphs as the observer and was able to more accurately differentiate between the age classes. The greatest difference occurred on the Kims only night. The camera captured nearly the same number of nymphs and subadults as on the paired night. However, the number of adults increased by a factor of 5. These were crickets that did not exit in the presence of a human observer with lights. Additionally, the majority of crickets exited the caves earlier on the night without a human present. In 2020, Kims captured an average of 479% more crickets than the observer. And against the historical average since 2003, Kims counted 282% more crickets. We also checked our 2020 observer against the historical average and found no significant difference. As a result of these findings, we made the following conclusions. We found that crickets are perturbed by humans with lights, that the use of cameras to count crickets is more accurate and precise with a replay capability. Cameras are less disruptive to the Karst community and safer to use. Because of these factors, we recommend the use of Kims as the preferred method to conduct cricket exit counts. I am ending my presentation with a few video outtakes which demonstrate Kims' ability to complete the mission where a human observer may have wavered. This concludes my presentation for today. I look forward to answering your questions during the annual meeting.